Welcome to the colloquium, today's colloquium for Halloween themed. My name is Maria Yang. I'm a professor in mechanical engineering, and I'm also interim dean of engineering. And I am delighted to be introducing our wonderful colleague, Karthik Ramani, today. He is our speaker, and I have to read your title because it's so long. Donald W. Feddersen, Distinguished Professor of Mechanical Engineering at Purdue University, where you have appointments in electrical and computing engineering and a courtesy appointment with the College of Education. And something you should know is, so you are a distinguished professor at Purdue. That's equivalent to an institute professor at MIT, which is the highest type of professor you can get at MIT. So Noam Chomsky is an institute professor, for example. So that's sort of the level that we are dealing with. I'm going to actually read because there's so many things that Karthik does. Hi, welcome. He runs the Convergence Design Lab, which looks at artificial intelligence and the physical world, merging human-centered AI, spatial intelligence, and immersive interaction. His work spans design and manufacturing, sports training, surgery, human-computer interaction, a lot of different topics that I think are of interest broadly. And he thinks about physical AI sort of very much from the point of view of design systems. He is a prolific researcher. He has published in top-tier journals across computers, computation, AI, human-computer interaction, engineering, and engineering design. And he's been an inventor and an entrepreneur who started multiple companies, including VisSeek, the world's first shape-based search engine for mechanical engineering, and Zero UI, which is a CES-awarded robotics startup. So very prolific. And he's a dedicated educator. At Purdue, he's inspired generations of creative engineers through his toy design and product process business model design courses. And he's held visiting positions at Stanford, Oxford, and Park, and here now, and just sort of fueling everything with your sort of unique vision of creativity, engineering, design, and sort of next generation technologies for, physical interactions. And I will also say that he is the coach of Purdue's table tennis team, and you incorporate this into your research, which is fascinating. And you also are very active in our table tennis, MIT's table tennis team. I think some of your team is here. Anybody here? Yes, I see. So good. So you're fully integrated, which is wonderful. Your talk today, Professor Ramani today will talk about ghosts in the machine when physical AI comes alive, which is so appropriate for Halloween. Well done. I don't know if you planned that. I just want to take this moment. I'm so glad you're here, and we're so glad to have you talk. So please join me in welcoming Professor Ramani.
All right. Is that good? Yeah. Thank you. Yeah. So first is miniaturization. We all know that we have shrunk things to small, very small dimensions, and also as a result of it, we have had to find places to put things, and so the Internet of Things and so on. Multiple places. Also, we developed the so-called computer design software, which I'll talk towards the end, and it turns out. Donald Feddersen was the guy behind Parametric Technology Corporation right here. Many of you know CAD tools and software, so he was a VC behind it. Thanks to him and the success of PTC, it sort of funds my chair position as well. But also, all of this has resulted in commoditization of both CAD and CAM. Machine tools went all over, and we have been able to produce all kinds of actuators, big and small, leading to many new technologies. But on top of that, also, the recent development that has surprised many, especially since the invention of the transformer in 2017, and its very rapid commercial success since 2022, the last couple of years, a lot of people are trying to use AI, but also develop new types of AI to do a lot of different things. So this kind of traverses both the language side and the visual side, and I'm going to bring a lot of it into this talk. But also it has led to being able to code very quickly and sort of, in some sense, commoditizing that part of CS undergrad program, and also being able to do math Olympiad problems and so on quite well, right? But of course, we're going to go beyond that. We're going to talk about physical AI and what can we do with all those things. But also robotics in general, the armed robotics, and more interest in humanoid robotics. All of these are all areas that sort of sit around many of the things we are going to talk about. So we're well past the information age, and we're sort of entering what I think is the age of understanding and using intelligence, perhaps in its very early forms. Some of my friends and colleagues, and even I, like to think of AI and the transformer architecture in the current form as sort of a steam engine of what is to come going further, right? I will be certain to say that in another 10 to 15 to 20 years, we'll just be looking back at the transformer architecture. And oftentimes I think, is it all it took to sort of get into human intelligence, the LLMs and so on? So certainly there's a lot of engineering behind these types of systems. But going beyond that, my view is that the opportunities really lie in the physical space, right? The so-called physical AI, which I'm not going to define that clearly, but I do want to point out that different people have different views of physical AI. Notably, I want to talk about just two key things here in this whole slide, which I sort of designed a while ago when I spoke about STEM impact in education at the US Senate. So the first one was perhaps the deep learning networks, the ImageNet and so on. The very foundations of it lied in image processing. But also, that kind of was very interesting turning point. And I was lucky that in my previous sabbatical, 2008 at Stanford, and before that, I had worked with Jan LeCun, and I was seeing early demonstrations of this. So we were very quick to get on to using deep learning. The expert systems before that did not interest me that much in terms of its potential, human-like capabilities. But more importantly, when the scaling of the so-called language transformer model, which was developed by Google in 2017, happened in 2022, it started showing very surprising results, right? Such as abstraction and many other things that we as humans might be doing, but do it very differently. And that surprised a lot of people, even researchers in the very same AI field. So that said, the language and scale, and a lot of it, a lot of the play has been scaling the transformer model. And the performance improvement surprisingly keeps improving by scaling it. I do think that it's going to be limited, but language and scale are not the whole story here. So the real story here, in my opinion, is that intelligence will demand embodiment and also context and physical interaction. And more importantly, coming from mechanical engineering, the context of intelligence, right? When we design things, build things, and make things, all that knowledge is lost, in the sense that in the end, you only have those artifacts and a lot of documentation, et cetera, that hardly get used beyond that. So I sort of think of physical AI as AI coming into the physical world. A lot of it, people talk about robotics. Maybe that's a very early view of physical AI, but I think we go well beyond it. And this was taken down at the MIT Museum, sort of emphasizing the gap between the human mind and what we do and AI as it is today, right? So clearly, the way we learn, we do things, and many other things that happen around us. We build things and so on and so forth using our body. We play sports. We do a lot of very skilled activity. All of that are, of course, what we kind of think of as embodied AI. So this idea of augmentation is not new at all. In fact, if you go to the MIT Museum, you'll also see in that same poster many other people that have contributed to very substantially to AI as it is today, right? I won't be going through all of that, but one of the early works in, of course, using interaction and interfaces, which is sort of central to what I'm going to be talking about, especially the interactions of humans and things, but also building AI systems that are appropriate for those interactions rather than just taking and adopting AI that might be existing elsewhere, right? And at that time, Doug Engelbart not only demonstrated the mouse, he also sort of talked about augmentation and a whole ecosystem around it, right? So I would like you to not think of these immersive reality technologies as those hardware gears that we wear and so on and so forth, which is important, but what does it do to us? How do we change our behavior because of these kinds of embodied technologies, right? And how is it going to influence many of the technologies that will come as a result of it? So certainly there's been a lot of commercial development and interest in this area. We have seen a lot of things come and go, players change, and so on and so forth. But all of you might have seen all these headgears, right? The virtual reality headgears, but also AR. How many of you have seen AR headsets? Pretty good. So you kind of know roughly what AR is. But also now you'll start seeing more simpler versions of those coming, right? Like the Ray-Ban glasses and some more recently released between Google and Samsung, just as early as 2 weeks ago. So these things do different things. Of course, the simpler ones are less capable, do very simple things. And of course, everybody wants to own our eyes now that we lost our hands and much of our other things to commercial companies. There's a lot of commercial interest in the past in this area. But also, there's a reason why a lot of those haven't succeeded, which you probably will guess from the rest of this presentation. But also creating these applications, right? Very costly, time-consuming, a lot of iterations, and back and forth movements, and a lot of even research labs that adopt these technologies do something, want to say, oh, let's make it easy to use. Let's make it intuitive. What are you going to make easy to use? What does intuitive mean in those contexts, right? These are hard things to do, as it turns out, partly because interactions with humans and a lot of things are not like just a finite set of a dictionary that we are using for large language models. It's much, much more infinite. And potentially, right, if you think of it being successful like YouTube, you're going to need hundreds of thousands of applications. We're not even close to that stage now. So that said, this human-centered computing, of course, has simplified in the sense that these devices are available. We have a lot of tools at disposition now, especially with the convergence of language models and visual technologies. It gives us new hope that we can push these further into reality, right? So scaling these at the end, right, for users and experts themselves to author is one of the challenges. And in the past, many of these, even larger companies were not able to solve these challenges and perhaps have given up to a large extent and then restarting it again, right? So the three pillars I'm going to talk about are understanding, which is sort of very much related to language, to perception and context. And next, I'll talk about authoring and interacting. So how can we think about both perception, understanding, which is kind of tied to each other. So perception, for example, if you're moving, we want an AI system to understand what I'm doing, recognize our actions, and maybe even say what I'm doing, right? So person is assembling furniture, for example, right? Textual description. So that's what I think of understanding to some level as an example. Of course, there's many other examples you can talk about. But generation is somewhat different, and the new generative sort of AI is sort of, if I say if a person is assembling a furniture, it should make a person assemble the furniture. And I'm going to show you that, right? Not just one action. I can give a series of sentences, and the avatar will do all those actions, right? Sort of more or less eliminating a lot of the in-between technologies which take us to create these AR and VR type of technologies. We don't have to put markers. We can do a lot of things simply by using some newer models, which I will talk about later in the talk. So as we move forward, there are three things perhaps you can take away from my presentation. So sort of watch for these ghosts in my presentation. So one is the embodied authoring. Can we teach machines by showing or talking to it, not coding, right? So there are two important examples I'll talk about there, agentAR and Caring AI. agentAR is brand new, just came out a few weeks ago. And Caring AI, I think, is a great example of taking and developing appropriate AI and then using it from a human-centered computing context, right? And then embodied design generation. Here, we are going to kind of see if AI starts seeing what we are doing, sketching, can it build with us? Can we make it after that, right? So two examples there, designfromX and just shape it. And then finally, of course, I can't avoid table tennis. That's my favorite sport. But not only that, when you try to push technologies using sports and athletics really brings it out. You're really pushing the goals. And then manufacturing and a lot of other applications become rather easy, right? And there's reality check here too. There's a lot of things that happen in table tennis which are common across all different types of AR and VR type of augmentation. Plus, you get to test it with people such as Andrea, who's here, part of the MIT team. So spatial computing, right, it's not 3D, it's not equal to 2D plus 1D, right? There are many hidden dimensions here, and that makes it very challenging. And oftentimes, it's not that obvious that we can consider these things while we create these systems. A very early example, one of my very early students, we have been in this space for a long time, much before the depth cameras at this scale came by. Very early system, actually Ian was a postdoc here at MIT soon after he finished, and now is the director of AI ML at Upwork. He did some very clever work. What he did was he sort of drew an analogy between geometry and recommender systems like Netflix and other things that many of you are familiar with, right? So if you like this, what else might you like, and so on. So it sort of used that analogy to actually create a like gesture recognition system, but also allowed it to work in real time. And it was one of the earlier works in this area. I'll sort of give you a very quick idea of how this kind of works. I'm oversimplifying it, but roughly speaking, right, you can take a hand, an image, a depth image of a hand, and sort of convert it into what we call activation features. Sort of think of these activation features as a set of numbers or vectors that would represent the pose, right? And then we want to find not only that pose, but nearby poses. So as I change my fingers and start moving it and turning it, I want to find nearby features. So you're reducing your search space there. So can we find it? Can I find it and can I impute the hand and render it in real time? Because hand is very fundamental to a lot of things we do, right? And if you can understand what we do with the hand and body, clearly you can create better interactions of humans with things and make the system behave better. So what he did was he sort of used that idea and took the activation features and then did reduce the search space and came up with very compressed forms of these vectors. He could do this in real time, right? So in that way, when you turn the hand on, when you move your hands, the system is able to infer and impute features. And in those times, this is a while ago, we were doing it in a fairly ordinary computer and working only at 32 frames per second rendering rate. You can kind of see that he was able to do a lot of different things. And it also seemed to be learning constraints of the hand and the hand movement and so on, which is sort of surprising, right? So sort of biomechanical constraints, which we often want to model more explicitly, the AI was starting to see and understand and learn that. But then you might consider saying that, well, this is more recent work. I pick up this bottle of water, or I'm behind this table. There's a lot of occlusion here. What is my hand doing now behind the bottle, right? You might guess, but can the computer guess? Can we do this real time? Oh, this is another clever piece of work done by one of my students, Sango, is currently a faculty at KAIST, working with others. So what he did was, this was one of the earlier applications of the transformer model. So sort of you complete a sentence. So think of that as an analogy. So if you have a paragraph, right, it sort of guesses what's going on. So kind of think of each of your digits as words. And if I'm occluded behind this bottle, the question now comes down to is, can I complete the sentence? And here, can I jointly learn both the hand with the language model and use the language model, which is working quite fast and quickly, to complete the geometry, right? So this was the idea that we proposed, and we showed that this can work very fast in real time, so which means you can predict occlusions and complete the hand in real time. So I'm not going to get into the details here, but basically the idea was you train it with the mass, right? And you can do this. You don't even need real hands to do it. You can do it virtually too. Once you do that, you're in good shape to be able to predict it. So what do we do with these things? So here are some very quick examples of applications of the hand for, in this case, like static provoking kind of a gesture. And here, this continuous kind of a response. So you virtualize the cup in real time and you're manipulating it. Can it respond with your hands? Of course, you can do a lot of these better, dynamic provoking type of gestures, and then more synchronous type of gestures, right? So you can do a lot of these types of interactions, but also creating these interactions, we made it very simple. So you simply connect your input and output while you create the program. You do that with your body, and then you're creating the ability for your response, action response type of framework to work in that way. But that said, I'm kind of going to talk a little bit about what happens to the body here. The best theories are ones that you can put to practice, right? So I'm going to show a little bit of the theory behind this, what we call info-GCN. So basically, the idea here, when you see a skeleton, you oftentimes just think of the joints connected to each other. But there's a lot of implicit knowledge held in the body as we move. And this implicit knowledge is sort of held between the joint here and many other joints, for example, right? So we kind of model this as an intrinsic topology of the body and use this intrinsic topology to sort of represent the body using some mechanisms called self-attention. So the idea of using implicit geometry and self-attention allows us to discriminate between various actions in a much finer manner. So in 2022, of course, it's a while ago for AI, this was the best skeletal representation covered by all other, compared with all other benchmarks at that time. So a little bit more about the self-attention, just to give you an intuitive idea, right? So here, for example, if you're doing these waving actions or pointing actions, you can kind of think of these other edges between your hand and the rest of your body as being a compressed form of representing. And we use something called an information bottleneck theory, which allows you to represent these more complex actions and discriminate them, separate them, or classify them nicely when you're doing actions in real time. But also, in doing so, we have the minimum amount of representation. It's very minimally represented, right? So it becomes very, very useful. So I'm going to jump now to from understanding to authoring. So authoring is more related to creating, orchestrating, adapting, and so on. So here, let's get back to building stuff and training people. Many of you here recognize the importance of being able to train people in using machines, doing a lot of other things that we do, train people and do it on a one-on-one basis. But clearly, you can't have an expert available all the time. Plus, you can collect the expertise of multiple people into one of these avatars, right, in some ways, and then have the avatar watch you when you're working on all these machines. The question now is, can the avatar adapt to you? Everybody has different forms of learning and doing things. Even a button press on a physical machine might be easy for you, but for my grandfather, it wasn't. He kept pushing it all the time, right? So there's a lot of different forms of interactions one may need spatially that we need the AI to understand and discriminate clearly. So what we do here is this was done by one of my students currently in Google, Shun, and many others. So what they did was they kind of came up with level of detail for these tutoring elements. And the idea was that if you can recognize lower level activities and user states, then what we can do is we can also understand the environment state and make the adaptation decision on how much to help people. Are they having difficulty? Are they hesitating? Do they know how to load the part? Turn the machine? Can they replace the coil? And as we go further, many of these ideas can be used for many maintenance, repair, and overall situations without actually authoring these kinds of things for each particular modality. So I'm going to sort of like, take a look at this. So the level of detail is simple next step, or you can animate components, or you can do a sub-task description, or, so the level of detail can be controlled based on what the system identifies in terms of what the user needs. So, so quickly, right, so this was during, basic CNN network is good enough. So we actually benchmarked this with all types of knobs, buttons, sliders, to make sure that it can work across all these different situations. And here is somebody loading a laser cutter. So it recognizes the action and also the subtask, and sort of starts either animating or start helping the user based on what they're doing, right? So it's kind of a clever adaptation of that. But also, of course, when you use a lot of instruments in your labs and so on and so forth, there's a lot of precision and detail needed in these authoring steps. So the question that we were asking there was, can we just by demonstration clearly understand and author the AR more automagically? So here, the author goes through the process, and in doing so, what we do is we also, of course, used a lot of, we created a very small micro recognition system for contact, and when your contact, whether it's persistent, how much you're turning, and so on and so forth. So using this, we were able to very accurately detect operations of turning and represent that directly into the representation that would go into the augmented reality system, and then it can, when you're actually doing these operations, it can tutor you, detect the operation, and also complete the operation. So pretty much you can generate tutorials automatically just by demonstration, and in this case, right? So here I'm going to transition a little bit into using the whole body here. So what we did here was, prior to our work in this area, when earlier work before this had already demonstrated certain types of models, such as if you say a person is walking using a handrail with left hand, it would animate that. But AI at that time couldn't do multiple types of actions one after the other. And this is very critical for you to, for example, create an augmented reality tutorial or immersive reality tutorial. You just want to not even demonstrate. We just type all the sentences. Can the avatar actually show you like how a human would show you to do all these different actions, right? So that was the idea. So we had to solve this problem of making the motion smooth across different types of textual prompts, and then generate smooth human motions across that, right? So actually the students were successful in doing this. So without getting into too much detail here, so you can kind of think of these tokens as being generated for micro actions here. So those tokens for these actions are generated, and you kind of create a code book which in a very compressed form, quantized form, represents the particular action. And during the actual generation between different types of actions, it generates a cross attention across them and smoothens the motion between these different types of motion. But also, we were able to represent these in a compressed form that we could do this across multiple actions. So there was substantial amount of development done there. But more importantly, how do we use this, right? So here, we sort of demonstrated this in a more human-centered context of actually loading machines or doing certain operations and so on. So the idea was, can we take something, let's say that you want to take object and load it into a 3D printer and do the settings and set it up to get the machine going. So multiple actions are involved here. So can we do this in a motion capture free way? Can it capture the context? So you just give the overall command to it, and of course the AI can decompose it into multiple sub-steps. You confirm that, and after that, in caring, what we did was quite interesting. What we did was we not only were able to generate the motion of the human to go and do different things, but we were also able to create the object models that you see that the human is using. And we didn't use any kind of SLAM techniques or other techniques here. We just took a single image of the object. So you go just look at the object, and using this single view, it is capable of generating a full model of the particular object, and we use that model for these multiple actions. So you can ask the user, go take a knife, take the knife and cut a vegetable or something like that. But more importantly, when the user sees this bottle, we recognize its 6 degrees of freedom and register it with respect to my head. So even if I lose contact with the object, or if I turn my head away, it retains the memory of where the bottle was kept, right? So what that does is it allows the avatar to recognize and go to different parts of the same room where multiple objects are kept, and sort of avoids complex techniques. So always I like to think of using the human within the AI loop to simplify all the tasks that AI has to do, and in that way you can achieve much more with AI. But more importantly, I'm going to sort of talk about agentAR, because what this does it converts the whole process of just talking and telling you or telling the AI system what do you want the application to be and what do you want it to do. So far, I sort of showed you different features. You might think, well, it's still all feature-based, still doing each things. And in this day and age when you can tell the flat AI something, why can't we do that in a physical manner, right? Why can't we just tell it, go do this type of a serve? Or why can't we ask the human to in this case, let's say that you want to make coffee, right? We just used the coffee making example. But more importantly, what we also did was, I'll come to this point in a minute. What we also did was we deeply understood all the prior applications that were created using AR in the last 5 to 10 years. We analyzed all of them, and we abstracted out both the back-end and front-end system. And the idea was, can we use an agentic framework to assemble and create and do all the back wiring and threading that we often do intentionally using coders and so on? Can it all be coordinated in an automatic manner? So you're not even creating these modules individually, but just coordinating all of them to do something very interesting. Curiously, I just saw a paper in Nature which used an agentic framework just published, but not for this, but for drug design. But the central part of the whole paper was the agentic framework, coordinating all these different experts in biomolecules and so on and so forth. And so I was kind of pleased that some things like this can go beyond just creating AR or VR applications. Okay, so let me quickly see if I can illustrate this. So I'm going to just. Can you hear this?
With just a sentence like, I want to learn how to make coffee, agentAR plans, builds, and launches an interactive AR experience instantly. From guided examples to user-created ideas, agentAR is changing how AR is made.
So I think this is an important step, simply because we were able to do some of our own authoring tools that we took a very long time to create. We were able to do things in a matter of hours or even minutes, which took us months or oftentimes even 8 to 9 months. So agentAR kind of like compresses the time. And partly, right, like I was telling you, the back end actually threads and the front end does all the rendering and a lot of the other things for UI elements and others that you normally would like to do. Sort of takes that entire TDM out of the authoring experience. So the backend does, as I was suggesting, the sensing, the perception, and a lot of the reasoning that is needed, and a lot of the gaze tracking, OCR recognition, many of the low-level tasks, physical simulation. For example, later I'll show you a table tennis example. We actually created some of our own experiences and things that were very time-consuming to see how this would work here. So lastly, I'm going to move to interacting. How are we doing on time? Okay. So interacting is more going to be tied to multimodality, right? The action, the feedback, the manipulation of objects, many of the things we do, right? Sort of jumping back to the training example where I was sort of suggesting that it's very, very difficult to have a one-on-one coach for every single thing for every single person around, right? So can we embody those experiences and have agentic coaches for particular types of expertise? So this was a project that we did with a person who wrote a welding textbook and a truck company and our lab, together working with some learning scientists. And it was one of our early experiments in trying to see, based on the goals of the learner, can we backward track and decompose the individual modules and recompose that in a forward learning manner so that everything that the user wants is very purposeful to what they are asking, right? So we did this for welding. But more importantly, we started thinking about how can we give real training experiences for real people with tools that are really realistic, not just the controller that you hold in the VR or AR experiences, right? That you well know. So what we have done, this is just out of our lab very recently. So you can kind of we called it Power Tool. So here you can reconfigure the weights and so on to have the inertial feeling for a real tool across all these several tools. As you can see, different weights, different behaviors, different vibrotactile feedback, and the feeling rendered to the person, both in a cutaneous manner as well as tangential and normal forces and so on, and the vibrotactile feedback. Can it be rendered across all these tools? In which case, we can start using this as a training mechanism for high precision operations, such as riveting, drilling, and so on and so forth, especially like in aerospace companies where one error in some of these operations can result in tens of thousands of dollars in loss and stop lines and so on. And this actually is a common experience that many of our sponsors see. So what we did here was we sort of took the real tool, and of course the machine learning part of it can extrapolate or interpolate between these different conditions, right? So for example, wood, acrylic, aluminum, and so on and so forth. And some of these hard materials, you can see that there are various types of responses you get, right? So can we replicate this while rendering back the vibrotactile feedback with a real instrument in your hand for high G-force conditions? And some of operations such as riveting and so on, when people go and start doing this in aerospace type of operations, they just get shocked, right? It's the first experience they have. So how real can we make it? So this sort of is a nice design problem. And here, it turns out that in the last few years, there are a lot of actuators which can render high G-force. So we combined 6 of them, sort of optimized both the compactness, the weight, as well as their vibrotactile rendering capabilities, arranged them in a way that you can get the actual feel of what's going on. So linear resonant actuators, ramps, and as well as eccentric rotating motors, all were used to give you a really good coverage there. So I'm going to kind of go quickly through this. So for example, so you learn the speed, the orientation, the material, and so on, and sort of let's assume that you create some kind of a lookup table, right? And then Power Tool, which is the device, actually is able to render these types of vibrotactile feedback in real time. It turns out that humans, when they feel these things, don't necessarily feel all the directions of rendering. So you can compress this into a single rendering vibrotactile thing. And this is a comparison between the frequency rendered with time, both from Power Tool and the real operations, right? So we were able to replicate, and actually this tool, we put it to use in industry before we published the paper. So the paper has just come out. But roughly speaking, you can kind of see that the AI not only does, I'm going to jump to the later portion. So it's sort of like, I'm going to move to the portion where yeah, this is the interesting part.
Up and down angles.
So actually, the AI comes and recommends you, and it surprised the industry people that it was giving them very accurate recommendations in terms of what you did and you didn't do. So we aligned the language model for recommending the operations with the actual operation, and it kind of almost tells you what to do at the end of your drilling operation. So I'm waiting for something like this to happen for table tennis, for example. Okay, let me see here. I think I lost this here. Slideshow. Okay, all right. Let's move past that. So yeah, so I want to bring it all together. And I'm going to give you a few examples to bring it all together, right? Let's see how we can pull it together and get my points across.
We now elaborate on an example
using
our system.
Yeah, I'm going to sort of jump this. So this is our table tennis system. So we have been working long and hard on this for a while, that we can detect ball position, human body position, and with all the things that I was talking about in almost real time, right? So we have brought that to a level that we could do that, but also we were able to sort of advise or recognize when target positions and the height above the net. We use very simple measures of targeting the ball to a particular location on the table, and also the player movement and trajectory, as well as the ball contact with the paddle. All of these have been areas that we have been working on for a while. But all of this was done, of course, in a AR setting, right? So I'm going to show you in a little bit of a time how we are able to take those, decompose the same skills that we have in table tennis into micro skills, and then have an AI avatar render it. But also I want to show you we can do similar things in design. Part of this early work was actually the work that was done before this in the same thing was co-authored by Professor Yang here in one of the ASME conferences. But more recently, what we did building on that was we again decomposed the design into smaller pieces. And in doing so, we also have a language model, which is coupled with the parts of the design, and we can do this all in image space. So you have plenty of images. You can easily do this in an image space. But more importantly, now we use the handle to change the features in the design using the text. So the text directly becomes your handle for manipulating the design. So it's almost like parameterized language. You can start playing around with this mountain bike, right? And then decompose it into various things that you as a designer might want to manipulate. The structure, the ergonomics, the color, the shape, etc. And then play around with it. But also what you can do with this is you can manipulate designs, combine designs, not that you want to put a wheel on a chair, but you can combine it. You can generate many designs. Now that you have lowered the cognitive load of the designer, we can look at multiple designs in parallel, right? Not just 6, maybe thousands, right? That's possible, and we have done that for other designs. And then you can visualize and reconstruct it, right? So all of this can be done. And of course, you might say, well, this is more like an industrial design task, right? How do I take this and do real designs? So what I'm going to show you now is to create 3D models of design. You just need to think about your shape and describe it in the air. That's all you need to do. So how do you do that? So one of the things we realized a few years ago, that when people gesture and they talk about something, the gesture and the language are coordinated. And this work is not new. People have studied this for a long time. But can we take advantage of that from an AI sense and coordinate both the tokens that are generated by your gesture, which I showed you in M2D2M and so on, and also the language, right? And can we coordinate these tokens in such a way that I need to just describe the design should come out? No need training, no need AI, no need large data sets, and so on. Can we do that? So before we got onto a design problem, because it was complex, what we decided to do this was first publish our work in a non-design setting. So we did this just for arranging rooms, furnitures, moving pictures, and so on and so forth. And you can read this paper in terms of the mechanics of how this gets done. But what I'm going to show you is its actual implementation. Actually, is talking with that. I'm not able to tell you what we speeded up the video. So that's all it took us to create a parametric design. And what we have been able to do is pretty much I replaced my first 4 weeks of my class. So now, if this becomes real, which I hope we'll be able to implement pretty soon in our own toy design class, the first 4 weeks, I can start having them do fabrication and a lot of other things, rather than go into this 14 deep menu clicks and these complex things that you have to do in CAD, right? So always, I used to teach this class for 10 to 15 years in the 90s. I was always frustrated because students forget and they'll not remember how to do some of these features. And these CAD programs are very complex. But also I didn't like the fact that it was called CAD, computer-aided design. It should actually be called DAC, design aided by computers. The computers shouldn't even be there. And I think as we go in the future, the geometric part of creating is going to be, already shown you, it's going to get more and more automated. I've shown you for simple things, but I think the way in which we can proceed with this is actually automating good things. So last but not least, I have to get back to, yeah, we are in good time, are we? 4 more minutes? Okay, we are going to get back to our table tennis, right? So here is AR, avaTTar. So what we have been working on is, can we transfer skills in playing table tennis from one human to a large number of humans, for example, right? And of course, in this case, Andrea is going to ask, it doesn't do top spin, it doesn't do all the kinds of things that I can do, but it's certainly starting to do very basics, right? For a 500, 600 level table tennis player, let's just get the forehand backhand push and the forehand backhand drives. So it was able to do all those 4 pretty successfully. I'm going to sort of get to beyond that. What can we go beyond that? But also here, one of the things you might have noticed that you play, but after you play, how did you play? What happened? A lot of these things just vanish, right? You don't remember what happened just a while ago. So there you can go back, and the ghost that learned from you, it sort of remains persistent, and it'll come back. And it sort of highlights some of your leg and arm movements and so on and so forth. So it starts correcting you for that particular ball with that particular trajectory. How could you have done better, right? Sort of you go see it and you walk around yourself and in a slower temporal setting, you can start understanding exactly what you could have done. So it starts doing what a coach does, right? Okay, not that we are trying to replace a coach, but always I like to think that we want to amplify one coach to multiple coaches or get coaching to people that can't get coaching. I'm going to jump here a little bit. I had shown you earlier that we can get ball trajectory and so on. This is collaborative work with Professor Yan Gu. She's a legged humanoid person, and so it's a great collaboration where the team worked very hard, very quickly, and a lot of it was completed recently. Perhaps we are the second, I would say, legged humanoid to use whole body control to demonstrate that using some basic reward functions such as height above the net and a target position, but also taking away a lot of the assumptions that it's getting very competitive here. So I would kind of say that table tennis is becoming to physical AI equivalent to what chess was for AI. Kind of think of it like that, right? So it's getting competitive here. There's certainly DeepMind, UC Berkeley, also colleagues at MIT. Many of them are sort of tackling this problem. I'll kind of like jump quickly here to finish up. So we can, of course, go from some of the motion diffusion models and others that I illustrated before to sort of training thousands of humanoids to do the basic things, right? And then transfer from simulation to real. Of course, there's a gap always between simulation and real. But this is some of our very basic work. And you'll see that certainly there's a lot more to go. But the motion of the humanoid is naturally emerging from those types of functions that I showed you. I had to get the table to a much lower position, but you can kind of see what it does. Last but not least, I want to end with some paddles. I've actually worked with one of your students in the past. You might recognize Maria, and he's actually featured down in the wall there as well. Influenced some of our thinking in this class, but you can see that using laser cutters and 3D printing, a lot of CAD happens in the first 4 weeks. A lot of training. I'm kind of wondering if we automated a lot of the bad parts of CAD and kept the human in control. How will this class look like 10 years from now or 15 years from now? So with that, I'm going to sort of finish up here. Let's see here. Get this to the next. I think we are at the end. So thank you for listening to me. Thanks to sponsors, a lot of my wonderful students that done all the work. Many of them are almost graduated or graduated and just gone. So we are going to sort of have a new slew of students come later. Perhaps, or maybe I'll stay with a smaller group. But yeah, thanks to all of them, and thank you for having me over for this colloquium.